Okay, good afternoon, everyone. Welcome again to this week's seminar. We have this week a speaker from University of Cambridge, Cengiz Hoca. Cengiz Hoca is a senior lecturer at University of Cambridge. His research interests are in computer graphics, vision, and machine learning or artificial intelligence with a focus on 3D digital reality. He worked as a research scientist at Disney Research and as a senior research associate at ETH Zurich before joining Cambridge. He obtained his MS and PhD degrees in computer science from ETH Zurich and completed a double major degree in computer engineering and electronics engineering at Koç University. He has been honored with several awards, including the Eurographics Best PhD Thesis Award, which is very prestigious, Fulbright Science and Technology Award, which is also very nice, and UKRI Future Leaders Fellowship. Thank you for joining us. Cengiz, the screen is yours.
Thank you. Thank you for the introduction. Hi, I'm Cengiz, and today I'll be talking about efforts, actually some of them, of course, like a subset of what we've been doing to achieve a form of 3D digital reality, essentially. So what I mean by this is basically creating digital models of the real world. It's basically the visual world around us. For example, humans and some other scene models, environments, fluids, etc. And of course, this is not an easy task, and we've been working on it for a while now. And I'll basically summarize the representations, the techniques that we've been using over the years to realize some of these goals. And actually, overall, this is a quite challenging task, which I realized when I was at Disney some years ago. So there, I mean, the artists, they spend hours and hours basically to model intricate details of 3D reality. It's like super time-consuming task, and I'm talking about thousands of artists working for months, actually, sometimes a year, to basically create a 3D scene and then animate characters, animate environment, and basically, like there's a humongous effort from their side, but also computationally super intensive, like in terms of rendering, in terms of all these applications and like all these things. I mean, I realize if you really want to realize 3D, a form of 3D reality that's actually realistic and high fidelity, then it basically requires a lot of people, a lot of computation. And the alternative to this has been basically capturing, right? So you can capture 3D objects, humans, etc. And this means, but now we need these large setups, and they're quite also expensive, hard to calibrate. For example, this one is actually called a light stage because of obvious reasons. And there's so many lights and cameras that are well calibrated. And basically then you can start capturing 3D objects quite accurately. But of course, I mean, both of these are not really practical. At Disney, this was fine. I mean, they spent years on this. Actually, Disney Research spent 10 years for face capture. And the Disney studios, I mean, of course, Disney owns a lot of different studios, including Pixar, ILM, and animation studios, etc. But they also spend actually decades developing these systems. Like they have artists working with Maya for a lot of years now. They have these capture systems that spent, I think, tens of millions of dollars so far. So basically, this is not practical. What we strive to do is basically making this practical for everybody. So creating representations for 3D visual digital reality so that everybody can actually have access to some form of this. And this has become even more important these days. Probably you've been following that AR, VR, I mean, especially AR, I'd say, is getting more and more traction. And VR, of course, there are all these companies like Oculus and some others that also push it forward. So creating content, 3D content, actually will be quite important for everybody soon. So that's why now there is this huge community, I think, around 3D computer vision / machine perception. Sometimes it's called machine perception, sometimes something else. But basically, we're kind of merging all these 3D communities into one. And that's what I've been doing as well. And today I wanted to do basically like an overview of what we've been doing and talking about a subset of the projects that I think is a quite representative subset of my and our group's research so far. And actually, I want us to start with basically like the overview of how I see this. So first and foremost, I think we should talk about models. So this is very important, right? So the right representation is very important if you want to move forward with a form of 3D digital reality that makes sense. And one way of creating these is basically is via authoring. So the creatives can author these models. And this has been the norm so far. If you want to create high fidelity representations of 3D visual world, then basically the only viable option has been authoring. And all these models they then give you a sense of reality. So we have the absolute reality and we have the kind of the fake reality via models. And then either via rendering or via sensing, we can go to projections from these. So when I say projection, I'm actually meaning it in a general sense. So it could be an image, could be a depth map, could be a combination of different features. But basically, a projection is an incomplete picture of reality or models that we have. And then from the projections, I define perception as going back to models. And my research is roughly in this area. So basically, I'm really interested in models and rendering, especially neural and differentiable rendering, and projections, basically different maps and different features that we can use, and finally going back from those to models as well, such that we actually can have a sense of reality in the computers, essentially. And one idea I've been exploring in the last few years is basically modeling each and every aspect of reality carefully, including geometry, motion, and materials appearance, and lighting, camera, and some scene semantics, and basically having the scene representation and then feeding it through certain algorithms, including rendering, and basically modeling this forward process, going from scenes to the final images or projections that we have, such that everything is differentiable, everything is machine learnable and semantically parameterized as much as possible, so we can actually backpropagate to all of these. So this is kind of roughly what I've been working on these days. Of course, this is actually quite nice because it merges our fields, right? So it's basically all these models we've been developing in the graphics community, and then we can make them differentiable. We can integrate them with some other machine learning algorithms and some differentiable rendering. And basically now it's an end-to-end process where once we model the forward one, we can also model the backward one. So it's kind of merging of computer vision, computer graphics, and machine learning, which is actually quite nice these days. So in this general scheme of things, I wanted to talk about a couple of interesting projects. And I want to start actually with something that I've been working on for quite a while, this 3D capture. During my PhD, even at the time, of course, I was more like a geometry researcher at the time, but the idea was also the same. So basically, we somehow get a 3D sense of reality. For example, we capture a point cloud, and then we reconstruct the surface. So then it developed into tracking, and of course human body tracking, because it's so important, especially for AR VR. And actually the project I wanted to start with also is also on this basically hand tracking. So in this particular project, I think it's really good summary of what the process is these days. Basically, carefully modeling different aspects of 3D objects and making them come together in a learning framework, and then basically simplifying the input gradually. So in the first incarnation, actually, of this hand pose estimation project, this started a couple of years ago. We said, okay, maybe we can just use a depth map first. So it gives us like a nice 3D cues for the pose estimation task. And what we did is basically, okay, we said maybe we can model this pose estimator with a neural network of a certain kind. Of course, there are so many different kinds. I mean, you could use an hourglass network, for example, or you could use a simple ResNet, etc. And we tried quite a bit of them. And then we said, well, of course, we could have direct supervision on the pose parameters, but actually it's really hard to get. At the time, so like 2 years ago at Disney, I deployed this OptiTrack capture system to track hands, but it was really hard to get accurate measurements, and you had to have markers, etc. So instead, actually, what we did is let's use these pose parameters and actually deform a point cloud, right? So we take these pose parameters, we take the point cloud, and basically we deform the point cloud. And then once you deform it, you can actually render it. And this, I think, is also kind of a good illustration of how we use differentiable rendering. In this case, it was a quite simple render. Actually, this is one of the first render I tried with some students. So this was a super simple resampler rasterizer. So you just resample the point cloud and you rasterize it into a depth map, right? It's like a super simple Gaussian interpolation-based rasterizer in the end. And then what we did is also apply the same process to the input depth map, because we want them to match in terms of the sampling density, etc. And then we basically compare these two. So this is the whole system almost. And this means now we actually don't need direct supervision for the pose parameters, which is actually a big plus. So as I mentioned, it was almost impossible to capture really accurate micro gestures with these capture systems, even the most advanced ones. And I'm talking about ones that actually cost a lot of money, and still you don't get the quality that you expect. And then one missing part in the system was actually some regularization, some notion of the fact that this is actually a human hand. And that actually we put here. Basically, we said, okay, not all poses are plausible because this is a human hand. It cannot have self-penetration. It cannot have certain angles. For example, the finger cannot bend backwards, etc. So then we put these constraints as well, this physical and human body constraints. And then the system, it was not trainable end to end. We could actually get quite accurate results. I was quite surprised at the time on the quality. So like just for context, actually the starting point of this project was basically for providing interface for artists such that they can actually hand do the animation. So instead of using the mouse and the keyboard, actually the keyboard pretty much stayed there, but instead of using the mouse, and they actually was using the mouse, using their hands to pose characters, because these are 3D characters and your hands also can move in 3D space. So that was the idea. And of course, if you want to realize such a system, it needs to be a quite precise system. So we tried this and it was already quite nice, and we were quite surprised at the time that it worked so well. But then we said, okay, maybe we can extend this to color images in terms of instead of depth, because depth cameras are nice, but not everybody, like not all artists can just have them. Of course you can shoot, but you know, it's like in terms of the cost, it's not really important, but in terms of the infrastructure, so they need to install it and this and that, it's not very convenient. So if you want to scale, we wanted to basically, we typically want to go to color images in the end. And then we did this follow-up project. Basically, in this case, we had a color image and we had a depth image. And what we did is pretty much the same. But in this case, the regularization, the inductive biases were given by a latent space that we pre-learned. So this is a pre-trained latent space that we trained with plausible human poses. So the good thing about that is now you can pre-train it with just plausible poses in a offline step, right? So you can capture, for example, using this OptiTrack setup with some markers, some hand poses. Actually, what we did is capture hands that are just doing random stuff, but also capture hands that grab objects and do some other like more realistic motions. And basically then we trained this latent space that captured all this plausible poses. And then from the latent space, we can get back to the pose parameters. So here the latent space basically replaces the constraints that we had before. And then from the pose parameters, we can basically do exactly the same. We have a shape that represented as a point cloud. We can deform the shape using the pose parameters, and we can resample rasterize and we have the depth map. And we can then do the same for the input depth map we have and compute basically the difference. So the thing is, in this case, the training requires us to have the depth map, but at testing time, we actually don't need it, right? So just a feed-forward path, you can see it's from the color image all the way to the pose parameters. Basically, it's just here, right? So from the hand to the pose parameters. So this means that now we can actually get rid of the depth maps as well. And for both of these cases, as you can see now, basically we had this idea, okay, part of the system should be networkized, essentially. And then we need to introduce inductive biases, for sure, because otherwise everything is a bit floating. So it's not clear, basically, which parameters mean what. But once you introduce this, it's much more clear for the system. And then we have this differentiable rendering component for both cases. And this is kind of a blueprint of what pretty much we've been trying to do over the last 3-4 years. But in this particular project, actually, as I mentioned, we could get quite accurate and precise results for hand tracking, especially when there are not many occlusions, I should say. When there are occlusions, then the results are a bit worse because we actually don't do essentially tracking, right? It's more like per frame estimation. And you will see, I just wanted to show a couple of results that actually most gestures are without too many occlusions. So for us, this was all fine. And for this project, one of the main, basically, goals, actually the main goal, I should say, is gestures. So basically, for different gestures, for example, one gesture could imply a click, etc. We want to understand what the user intends to do. And in this case, actually, it worked pretty well. So, and then we said, maybe we can also use similar techniques for some of the shapes, for example, human body shapes. And we did these papers on selfies, basically, like from a selfie, can you capture your body shape so you can understand if you're, for example, gaining weight, or if some of the measurements that you do are actually accurate for cloth fitting, etc. So this is actually a paper that's quite related to what we did with the hands. And then we also extended to some a bit more, let's say, exotic cases. For example, for garments, this was actually quite hard project to do because garments, of course, can deform in much more ways than a human hand can do. And in this case, actually, we simulated a data set of garments. So this was trained all on synthetic data set because it's really hard to capture actually garments. And we also had a subset of clothing that we wanted to target. We had shirts, we had some skirts, but of course you cannot capture everything. And this, I think, also gives a good idea of the challenges. So for if you constrain yourself quite a bit, then you can get nice results. But if you start, having a lot of degrees of freedom that multiply, then it's becoming exponentially harder actually to achieve good results. And in this project, that's why we wanted to have like a huge data set. Actually, this data set, I think, was generated in 1 month, like 1 month of GPU computations, just to simulate and render. So it was much harder. And one, I think, cool application of all this was this collaboration with VZT. At the time, it was called something else. And the idea here is basically having this fly-through videos. So you have certain views in the scene. In this case, it's a soccer game, and you want to change the view. Basically, you want to see the same game from different angles. And this was basically a collaboration that lasted for 3-4 years. And the idea was, instead of using cardboards, which was what they were using at the time, just like a cardboard per player, we could use actually estimated human shapes and poses. And this is especially important for close-up shots. If you want to change the view for a close-up shot, you want to make sure that the interpolation of the players are correct. So I think this was all fine, like with this company before during my ETH times, and then at Disney, actually, all these human body tracking stuff were quite instrumental. So I like this project quite a bit. And as I said, I mean, this I think serves almost like a blueprint of what we've been doing over the years. And one important component of, as you already seen, of all this pipeline is this rendering component. And this is something I've been really interested in over the last 2 years, I should say. So we published a paper in the first one was in 2019, and now I'm working on a couple of more. And the idea is basically kind of reinventing rendering. So we, of course, know how to render stuff, right? So we know, given a scene definition, how we can render the scene such that it's photorealistic and has all the intricate details, etc. But now the thing is we want to make it machine learnable. This is like the main difference. So we kind of re-implement some of the classical rendering algorithms in a differentiable way. So there are essentially three properties. The first one, as I mentioned, should be machine learnable. And second one should be much more efficient. And this is very critical. And at Disney, for example, sometimes rendering a scene could take a month, which is a bit strange, but of course not all scenes. But in this case, especially if you want to have global illumination and certain effects that require a lot of time, so you either want to approximate them or you want to have some way to efficiently basically have them instead. And it should be task specific. So far the renders have been general in the sense that you get a scene definition, and basically this is the same render you apply to all scenes for all tasks. And the task was just one, right? Basically getting the pixel colors. But now it's not like that. So now we want to use it for the backward process, the inverse process, which means that now we have so many tasks. So it could be a depth map estimation, could be tracking, etc. And it should be really task specific in this case. And there's a whole spectrum of this differential renders. We could go from simple rasterization. Actually, simple rasterization is not that simple. So just to say, but basically, conceptually it's simple and it's a bit more efficient. But you can go all the way to actually path tracing, which is much more involved. But then you can get global effects as well. And there is now the whole spectrum of renders. And I think the one render that, again, serves as a blueprint of what we've been trying to do, and it's also very important in practice, is basically this point renders that I've been working on. So I wanted to briefly talk about that. So in this case, what we want to render is basically points. And each point you can actually represent with so-called splat. It's basically a disk that's orthogonal to the surface normal. And you kind of project all these disks onto the screen space and blend them. So this is kind of the idea. And this is, of course, an old technique called splatting. And the idea I had a year ago was, okay, I mean, this splatting is a nice technique. Can we make it differentiable so that we can directly render the point clouds that we have? For example, for the hand tracking project, instead of using a super simple rasterizer. Right? And of course, like if you have such a representation with like the splats and you want to blend them and rasterize them, there are always cases where the process becomes discontinuous. And again, this really serves as a blueprint of the challenge or in all the differential rendering projects. In this particular case, assume that you actually have a splat that is not visible at the moment at this point X on the screen space, and you now start moving this splat. As you move it, of course, at some point it becomes visible, and then it becomes invisible again. So basically, this creates a discontinuity. And once something is discontinuous, of course, it's a bit harder to make it differentiable. And this is always the problem. So basically, the renderers themselves, if you don't consider geometry, if you don't consider occlusions, then it's all fine. You can actually implement, re-implement, for example, in PyTorch and TensorFlow. But once you get occlusions, once you get these discontinuities, then you run into problems. So this is always the case. And the whole differentiable rendering paper theme is on basically how can we make this occlusion function differentiable. This is the whole thing. But once you can do it, actually, you can run some interesting inverse problems. For example, we did actually multi-view reconstruction and denoising for geometry. And in particular, we did this with point clouds, such that, you know, it's topology independent. So you can actually start with a sphere and you can deform it into a torus, for example, which was not easy. Actually, it was almost impossible with mesh-based approaches. Now I'm actually working on some other approaches which also utilize implicit functions, but basically the idea is always the same. You have a representation for a geometry, for a scene, for the textures, and you have these different views that you render your scene from, and if you make everything end-to-end differentiable, then basically you actually can run this inverse process. So the next thing actually I want to talk about is the scenes themselves. So this was more like the differentiable rendering part, but also there is the part where we want to model different aspects of scenes. And in particular, I'll be talking a bit about geometry because that's what I've been focusing on over the years. And as I just mentioned, actually, there is now this fundamental kind of distinction between implicit and explicit representations for learning. Some people like explicit ones like a point cloud and meshes, and some people go more like for implicit ones, especially with neural network-based functions. And I've been actually working on both. So basically convergence, given a point cloud, how do you go to implicits? Given implicits, how do you mesh it, etc. And well, one thing that's really important is that for all these cases, you have your right representation. I'm not fully convinced that there is one right representation, but you need to be careful. If you're not careful, then you can actually run into several problems that are slowly being well known. And in geometry, we know actually quite a bit of them. But once you have the right representation, for example, we've been actually working a lot with point clouds because my background is a lot of my background is in point clouds. So once you have the right representation, you can actually do interesting stuff. So let's say you have a representation, you have a renderer. Now you can actually use the rendered, in this case, image or some projection to do, for example, classification of your geometry. Or you can actually do so-called consolidation, basically making your geometry nicer, so denoising, removing outliers, etc. And of course, you can also combine these two. So you can say, okay, once I know what class this object belongs to, I can also use it in some other tasks. And in the end, we could get actually much better representations and corresponding labels for geometry. Just want to show you actually two particular examples in this theme that I think are quite actually representative of what we've been trying to do. And basically, it's always the same idea, as you will see. So we start with some representation. This is, let's say, in this case, a point cloud. And we first estimate a certain canonical form. In this case, we have some canonical view. So like, it's in this case, just a basis. And then we run this representation through, again, a differentiable renderer. In this case, I'm just using a super simple resample rasterizer, as I mentioned before. And this basically gives us a map. In this case, it's almost like a depth map. And then we can actually use any denoising algorithm that normally would work on image data and back project this to 3D using the same view parameters. And basically, this gives us the output patch. So as simple as that, right? So you just have the right representation, the right differentiable render, and you just get your system out and end-to-end train it. And actually, this was quite nice. 2 years ago, we published this. I mean, we got quite interesting, nice results, and I was really surprised. I mean, I spent quite a bit of time on this problem in the past. And actually, the left one is still state of the art, I should say, from my PhD thesis. And what we could get, this simple learning is much better than what we've been trying to do, basically by carefully formulating this implicit reconstruction problem. So it was quite nice, interesting learning introduction for me for geometry. And then I was not convinced actually. I also wanted to zoom in and look at the normal maps. In this case, I'm just plotting the normal maps and some of the maps from the geometry just to make sure, we actually getting these results. And it was really the case. I was quite surprised at the time, but I think this really serves as like a good example of, what you can achieve with learning. And then of course you can use it with also real-time applications. In this case, it's actually captured from some depth cameras, which are quite noisy. You can use similar reconstruction techniques for getting nice geometry out. The other project I want to briefly mention is this geometry classification one. In this case, we again given a point cloud, and we again do view estimation, but in this case, we have two view estimators. So we get actually two views out. And again, we run it through simple differentiable renders, and we get two depth maps, and basically then you can actually do view pooling. So you first estimate classes, and then you do actually pooling of these to get out the class of this object. And this was again published, I think, 2 years ago, and we could get quite accurate results for point cloud classification in this case. So it's almost the same system as you just seen, but in this case, we use it for classification. And one, of course, byproduct was also that we could actually estimate the views that are most and least informative, right? So some views actually could give you quite nice labels, some not so much. And these were consistent across different objects if they belong to the same class. So this is also a byproduct actually of all these architectures. Once you carefully model different aspects of your scenes, then you get these out as byproducts. This is, I think, also one cool feature of working with models that you're seeing models where you actually have inductive biases here and there. So one problem I want to briefly mention, because this is sometimes a bit overlooked, I feel, is the sampling problem. So for all these representations I've been talking about, for all the renderers that I've been talking about, actually this problem is there. And I've been working on this problem for quite a bit, from theoretical perspective, but also practically at Disney and before. And if you think about it, everything in a scene is actually sampled, right? So this is what I call the sampling problem. So we work with discrete structures, we work with computers, and we want to represent seemingly continuous structures with this computer based algorithms, like the digital technology essentially, right? So this means everything needs to be sampled, including geometry, textures, cameras, motion, lighting. And if you're not careful with the sampling, then you can easily run into this kind of problem. So this is actually a scene I took from Pixar. And basically you get a lot of noise, outliers, and artifacts. And if you're careful with sampling, instead you get something of this form. So it's very important, this sampling problem, and it's becoming even more important actually for machine learning. And I've been working on this, as I said, for quite a bit, based on this theory of stochastic point processes. I'm not going into too much details, but I just wanted to introduce the concept because I think it's quite powerful actually. So the idea here is that you have a point process, a generating process that generates multiple distributions sharing common characteristics. So basically you get infinitely many distributions, but they have similar characteristics, and because they actually were generated by the same underlying process. And kind of in a nutshell, let's say, the idea is capturing correlations of random variables that you define in space. For example, if you define on set B, you can say, well, my random variable is the number of points that fall into this set. In this case of 3, for a different point distribution we generate from the same point process is 5, and maybe for another one is 2, right? So instead, random variable, if you fix the B in space and just change the distributions that you generate from the point process. Now you can also define joint distributions. If you have 2 sets in space, then you can also define this joint probability distribution. And basically you can go also higher order and represent everything in terms of these correlations. And then what you can do is apply this theory. So as I said, I'm not going too much into details, but it's a quite nice theory, point processes. Then you can apply it to actually all kinds of structures, including geometry, which I did some years ago, and such that you get much less points for the same quality, or for random effects such as depth of field, motion blur or depth of field. And you basically, for all these cases, get much more improved results than what you would normally get with regular sampling or normal sampling. And in this case, actually, people typically use log discrepancy patterns, and we could show that you can get much more improved results if you carefully fine-tune your sampling to the effect that you want to capture. And then we also applied it to geometry synthesis. Basically, almost the same theory applies in this case. And environment modeling. So, for example, you want to model the distribution of entities in a forest, like trees in a forest. You can actually use exactly the same theory. So this works for all cases where you sample structures in your scenes. And this is like, it's always the case, like you always sample. So I think this will become more and more important, especially if you, as you want to render scenes more efficiently and with much less noise and artifacts for machine learning frameworks. So finally, as the final part of the talk, I wanted to a little bit talk about, these fundamentals that are very important for realizing this system. So when I say fundamentals, basically it's fundamentals from machine learning. So I've been working on some of these because actually they were important for our projects and practice. And I wanted to just mention a couple of them, basically 3 of them in this talk. And they are basically first understanding what we do, which has been quite a challenge over the years. I should say, like many students, unfortunately, they actually don't fully understand what to do anymore. I mean, when I was a postdoc some years ago, it was not the case. And then once the machine learning started to penetrate into our fields, then I saw the trend quite obviously. And so one important thing is that we understand what we do, otherwise it's not science, right? So this is the first thing I wanted to talk about. The second thing is briefly optimizing neural networks, making them a bit faster, a bit smaller. And the third one is basically making them converge a bit faster, right? So the first one is more like understanding the second and third one is more like optimizing neural networks. So the first one, understanding them, sometimes called interpretability. And I've been actually working on one particular version of interpretability. This is called attribution techniques. And just to understand what interpretability is, imagine that you actually doing a classification. So I think it's easier to understand it for a classification problem. For example, let's say you're classifying X-rays. And the output is either normal or abnormal, right? So for example, this one is not normal, so because maybe there's some breaks, etc. So this is actually a real application. So this is already deployed. This is all good, and you can actually achieve accurate results and this and that. But what did you actually learn? So what was the thing that made the classifier successful? Not so clear. Typically. So is it based on the arm itself, or based on some other things, some other structures that correlate with the arm? For example, there's 2 lines that happen to be there for most of the images in your data sets, right? This is very important to understand. And in general, it's very important to understand which parts of your network are actually contributing to the output. So one particular way of quantifying this is via so-called attribution techniques. In this case, so let's take again the classification example. We take a particular input, a particular pre-trained network and output, in this case a class, or class probabilities, and we take all these into this attribution technique, and basically we can then take out a map, essentially. So this is an importance map. You can define it on the input, as we did in this case. It's like a heat map, like red means more important, white means less important. So which pixels actually contribute to the classification output? This is basically what it's giving you. But in general, you can also compute these importance maps for the nodes in the network. So you can really understand what's going on in the network, which part is actually not contributing, which part is gradually contributing more as you train, etc. So this really gives you an understanding of what's going on in the network. So what we did in this context is basically we first investigated quite a bit of different techniques, hundreds of them in the literature, and we proposed actually a unified framework for all these first. I mean, not all, but most of these. And then we actually introduced something called deep Shapley values. This is a game theoretical concept that we adopted and basically extended to deep neural networks. It gives you the contribution of people in a coalition. And I wanted to briefly, explain this because I think it's interesting. I mean, of course, I'm not a person that works in game theory, so I had to learn this as well, and learn how people have been using it, what extensions there are, etc. But the concept itself is actually quite simple. So let's say we are a coalition of 3 people, as an example, and we actually produce something, so something of value. In this case, we produce like a gaming device that has price of $100. Now, if you want to understand what your contribution is to this product, what you can do is you can add yourself and remove yourself for each and every subset of the other people. For example, you say, okay, what will be the price if I would remove myself and just 2 people were left, and you subtract, these prices, and you do it for each and every subset. And you basically then sum up all these differences. And this gives you your contribution to this particular product. So this Shapley value idea is really nice, theoretical, well-founded, implementation in very meaning that it's independent of how you implement your interpretability algorithm. But unfortunately, it's actually quite slow. It has exponential complexity. It's an NP-complete problem in a certain sense. So basically, it has all these nice properties except efficiency. So that's what we introduced. So we said, okay, can we make it efficient and run it in polynomial time? And we introduced so-called deep Shapley values. And the idea is actually given a neural network and modeling a distribution of subsets. So we first start with a distribution of all the subset of pixels, in this case, on this image. And we construct a dual network to the original network such that we can pass this distribution through and get at the output a distribution that we can use to approximate Shapley values. This is like, in a nutshell, the idea. Of course, it's a bit, there's some details I'm glossing over, etc. But this is essentially what we did. And this construction of the alternative network, like the new network, is actually also pretty much automatic. So you don't need to hand do it, like, you don't need to hand tune any parameters, etc. It's basically via probabilistic networks, and basically you already get this distribution out, which you can use to approximate Shapley values in polynomial time. And then we applied it not visual data, but to so many different types of data, and it worked well for all these cases. Then we said, okay, we can use maybe pretty much the same technique with Shapley values for measuring importance of nodes and pixels, etc., for pruning, because once you know the importance of a certain node, you can say, well, this part is not so important, I can prune that part. And once we did this, a couple of months ago, we could get also quite nice results in terms of pruning. So basically, pruning means reducing the network size, deleting some nodes in the network, for example. And we could actually really prune and still get highly accurate results. So the last thing I wanted to talk about very briefly is actually what we've been doing also for making networks learn a bit faster and converge to better optimums. And in this case, again, I'll just take a classification problem. The idea was let's say we have this actual boundary and the current boundary between these 2 classes, class 1, class 2. And normally what you would expect is this gradient, right? If you would have a lot of samples and you could sample the boundaries nicely. And this is actually really an expected value of your loss. But what we do instead in learning is approximate this with some samples. And then once you do an approximation with samples, you always have a bias and you have the variance of this estimator, right? And the idea of this last project I wanted to talk about was basically carefully shaping the bias and variance as you train with sampling such that you actually get more stable training. So, and then we again apply it again as this last in the last project, we applied it to different types of data as well beyond visual data, and we could get quite nice results. So yeah, this is pretty much all I wanted to talk about. In summary, I really believe in this future where we can now have a digital reality for all. And I think these these models and projects, they're converging nicely in the community. And as I mentioned, there are so many different components that come together now. The communities are merging. And yeah, I really believe maybe in 10 years we will have, maybe 5 to 10 years, we will have actually from our devices, for example, cell phones, quite accurate and high fidelity models of 3D digital reality.
Okay, thank you, Cengiz Hocam. That was a really nice presentation, really inspiring. We had a chance to see the issues of the different stages of the of digital rendering, digital reality. That was really nice. Any questions from the audience?
I can, not a question, but a comment maybe.
Please.
Thank you very much, Cengiz Hocam. It was a really nice presentation. I work on human pose estimation, and especially in 3D pose estimation, there is really there is a need for 3D pose estimation training data in the wild. Okay, so the existing data sets are captured in lab settings using existing motion capture systems, but when you go outside, unrestricted environments, lighting conditions, you cannot capture really 3D ground truth data. And one solution may be rendering realistic people in realistic environments. So this could be a really, I think there's a gap here. So this gap needs to be filled. And in the other part, differentiable rendering, I think I find it very exciting. It has already opened a new area in computer vision in recent years. People call it inverse graphics. So starting from a 2D image, you arrive at a 3D representation, and then once you have that, using the differentiable rendering, you can generate new data, and this can be used as new training data, or it could be used as a validation for your 2D to 3D model. So I find really exciting these things. So not a question, but
Yes, me too. I mean, so as I mentioned, actually, it's really interesting. We're kind of re-implementing renderers now, Python or TensorFlow. Always there's this occlusion problem, of course. But one thing I realized also should be really task specific. I mean, something that I actually very recently started thinking about, maybe like a couple of weeks ago, depending on the application. For example, for faces, occlusion is not so important. I mean, self-occlusion, there's almost no self-occlusion in the face. But for the hands, it's a completely different story, right? And differentiating through visibility, through occlusion, it really depends on your representation. I mean, if you point out, as I tried to show a bit, the splats, they appear, disappear. But if you have implicit representation, its parameters are not directly mapped to such occlusion. So depending on the representation, actually, the way you model occlusion changes. Also for global illumination, of course, is a completely different story. Now I have a couple of projects on that. And they're like having certain effects, for example, like post-its are super time consuming. So do we really need them, or what kind of correlations we need to exploit in general? For example, do you want to see around corners, via soft shadows? So, this kind of stuff. I think we should be really task dependent what we want to capture, what effects we want to capture, and what representation we want to use. There's something I think that's not there at the moment, actually. Maybe it's like a good topic of research. Making these renders a bit more task specific.
Yeah, thank you.
Cengiz hocam teşekkürler. Thank you for your nice presentation. Sorry. Did you find the Laplace-Beltrami spectrum useful at any part of your studies, like the point cloud processing or the sampling part? Can we give us some hints on them if you use it?
Exactly. So actually, in my second or third project ever in my life, it was a sampling project. I used the spectrum, Laplace Beltrami spectrum. I mean, not the spectrum itself, actually. Well, yes, I started from the spectrum. In the end, the algorithm did not depend on the Laplace Beltrami, actually. It was more like a kernel-based, a heat kernel-based technique. And then I kind of left it there for a lot of years. But actually, I recently picked it up again. As a matter of fact, we have a project going on, and I will be very happy to discuss further. That we try to go from operators back to geometry using learning. And one particular operator we'll be considering is basically Laplace Beltrami, because it's like it's intrinsic. It's up to isometry defines the geometry, right? So this is actually quite useful for example, for human bodies, where we get isometric or almost isometric deformations. And actually, it worked pretty well. I could also share like a GitHub repository. The student, actually, he was an intern. Hopefully, he will start a PhD if he is accepted soon. But what we did is we implement this heat kernel, which is very related to Laplace Beltrami, of course, and try to get the geometry from this heat kernel descriptors. Actually well-known in geometry, to have a good representation of geometry. And this normally not very trivial if you want to do it mathematically, because like there's so many nonlinear steps in between. And I tried it actually. I tried 5 years ago, I think, or maybe 6 even. I was discussing with some geometry people, and at the time I was like a more like pure geometry person. Really like mathematically how we can get from Laplace Beltrami spectrum to geometry, Laplace Beltrami itself to geometry, heat kernels to geometry, but we couldn't find a good solution at the time. And then like a year ago, I said maybe we can throw some learning algorithm on the problem, and it seemed to work so far. Of course, we need to do a lot of experiments, and it's at the moment a bit more early stage, and I think using some trivial structures. I think there's a lot of room for improvement. Maybe it will take a year or so until it really converges. But the initial results are promising, so you can really use it for learning geometries. I'm still a bit doubtful about the applications though. I mean, theoretically, and in terms of research, I think it's interesting. We can use it for human body capture, for example, or maybe deformation transfer, maybe defining latent spaces. But in practice, I think still the other algorithms might perform a bit better at the moment, because people have been like making them perfect over a lot of years. And there's descriptor-based ones that I'm thinking of. Maybe it's more like on the research side for the next couple of years.
Yeah. Okay, we can even discuss further. Thank you for your information.
Of course, it would be great.
Okay.
Maybe I can ask a question.
Yeah, sure.
Cengiz Hocam, I'm Gökberk Cimbiş. Thank you very much. Super interesting talk and lots of interesting things. It's also full of content. There are so many things that would be very nice to talk about in detail, but something that's bugging me at a high level, not from this talk, but like in general, like something that I usually ponder about. So something that we've seen in, for instance, natural language domain is that if you really scale up models, they behave in very interesting ways. They don't suddenly become cognitively active or conscious or whatever, but they start to talk very nicely. So thinking about the same pattern in the geometry modeling domain, how much geometry do we really need? Like if we take these generative models and really scale up crazily, I don't know, 100 CPUs and 100 years of training in one GPU time, let's say, would we end up with geometry algorithms or rendering algorithms that are better than what we currently have?
Yeah, I mean, it's a good question. Of course, like, do we really need geometry? Probably you've seen the paper NERF.
Yes, but not in detail. Yes.
Yes, basically a view interpolation paper. But what they do is they actually have a variance field representation, meaning that at each point in space, you compute the light vector, essentially. That's how much light is passing through that point. So, and then this was seemingly sufficient actually to represent the scene. Of course, like theoretically it should be, but I was surprised to see that actually as an internal neural network representation, that was also fine. But there are so many other works actually that use, in the moment, more like implicit functions for representing geometries, and that also seem to work quite well. So for me, it's a question. I mean, how much geometry do we need? But my intuition is always the geometry we need for warps, basically. So you cannot really work with convolutions. You need to first kind of have a base which does the global warping and basically making your pixels go to the places that they need to go, and then you can optimize for the pixels themselves. So this is the geometry level I think we will always need. Sometimes people induce this via optical flow, right? So you just warp the image plane, and sometimes people do it via geometry. And then the other question for me is okay, we have the geometry, but in the renderers, do we really need the full forward process, as I described a bit, or can we get away with so-called neural rendering? So I think a simple but interesting idea that people have been working on over the last year, pretty much is neural textures, right? So per point, you have like a vector that defines some kind of texture. It's actually not a real texture. And you just interpolate essentially rows with a neural network to get out the final, for example, pixel colors. So it really extends from the normal textures to so-called neural textures, because normal texture means, for example, you have a normal map, so it defines something really tangible on the geometry. But neural texture, you don't know what it is, but the network is supposed to interpret and give you the output. And this is also, I think, an interesting development. I mean, my intuition there is then, if you have actually good models for what you want to render. So for example, let's say you have a hand, and you know there's skin, and the skin has certain BSS, SDF, and you know how light interacts with the geometry, etc. So if you can model these, then I think you should use that. If you cannot, if you want to be a bit more general, if the number of if the degree of freedom is too high, for example, you want to capture all models like tables, hands, and windows, and basically you have all these material indices and models that you cannot just put in and expect that the network will learn the parameters for, then I think neural rendering makes a lot of sense, because it gives you a bit more general framework. I think I might actually have missed a part of the question. So you mentioned also generalizability, right? So how these scale, I guess, right?
Yeah, it's more like this. So if I have like a 3D model of the scene and run the state-of-the-art renderer with all texture, etc., all the details, we end up with, or if we do ray tracing, we end up with something that looks pretty nice. But well, I'm thinking about, can we end up, or can we have something like this that's completely trained and perhaps gives us comparable or better results with much faster inference, let's say. And in this process, how much like explicit geometry, that's basically the essence of my question. And I think you already answered that. It's, practically, it makes a lot of sense to use what we already know. But it's also curious, where will it be in, let's say, 10 years from now, in terms of rendering algorithms that we are using. Maybe we'll end up with completely neural things that are rendering games. But it also looks very tough because we have this sets of objects representation. It's not like, you know, simple image-to-image translation task or whatever. It's more like I have this whole scene and I want to render it, and human brain doesn't seem to be very good at it. So a reference.
Exactly. I think we are very good at recognizing, but not very good at generating, right? So I mean, if you tell me, I mean, model or like draw or maybe explain like the room in detail, it's really hard, right? I mean, if you just see it for once, if you of course see it every day, then it's still a different thing. But actually, there's also something that maybe I cannot speculate too much on, because now I started working a bit with neuroscientists to understand how the brain does it. Of course, they don't also fully understand, but they understand much more than us, probably. So, I mean, actually, we were also discussing with Sinan. They had also this super nice paper on understanding how the cortex is actually processing, right, visual data. And I also discussed with some other neuroscientists. It's not very clear, but it turns out that the low-level vision and high-level vision, it acts like what we have in neural networks, but the mid-level vision is a bit different. That's what they told me. I'm not an expert at all, of course. But yeah, there's something I really want to understand, how the brain is representing. Is there any geometry in the brain? I think that's something to see. I mean, some clinical people, like for Alzheimer's disease and Parkinson's, they actually told me when you have Parkinson's, for example, or actually Alzheimer's a bit more, you lose the sense of where you are in a room, for example. So I think there's some geometry in the brain, but how much and in what form? That's certainly something super interesting.
Thank you.
Thank you. Maybe we can stop recording and switch to the more informal part. Thank you, Cengiz Hocam, again, and thank you everyone for joining. We can stop the recording here, and Cengiz Hoca will continue giving us answers to really interesting questions like the meaning of life. So let's stop recording.